when the wave is moving, it is a moving wave front rather, and that we call as a surge. And of course this has some other name like bore. When it is in sea, in estuary, then we call that as a bore. So then we were just starting the governing equation of unsteady flow. And when we did cover the when we started with this unsteady flow equation, governing equation, that was particularly for say gradually varied and shallow water wave equation of unsteady flow, and we were talking about continuity equation, in fact which we have discussed already in our class when we were starting our governing equation, very maybe in our 5th class or 6th class. And then next equation, that is the equation of motion. Generally we need 2 equations for solving the problem of unsteady flow, and that is why the continuity equation and equation of motion is used. And equation motion we can get again in different forms. We can develop this equation starting from different principles, like say from energy approach we can develop it, or starting from the Newton's equation of motion we can develop it. And then here we were just starting to show how from the energy approach we can develop this equation of motion. And of course here finally we will be developing one form of the governing equation, and we can have several different form of this governing equation. And we were writing that equation for this sort of flow, say section 1 and 2, say this is the datum, and we were considering a small section, say del x, and then say this is z1 y1, then v1 square by twice z, and this is z2 y2, and then v2 square by twice z. And then there is energy loss that we could get some expression for that. This energy loss we can divide it into 2 parts, say HF, loss due to friction, and loss due to acceleration, okay. And then equating the energy between section 1 and 2, just recall we did that in our last class. So we could write that Z1 plus y1 plus say v1 square by twice z is equal to z2 plus y2 plus v2 square by twice z plus HL, and this HL that we can write as HF. This HL is nothing but HF plus HA, friction loss plus loss due to acceleration, or work done, energy loss due to producing that acceleration. So this part also we derived in our previous class. And then from this expression what we can write, putting those expression for HF, if we remember or if we recall, then HF we got as, this is from friction slope. Say if friction slope is SF, then SF into delta x is the total friction loss. If friction slope is SF, say friction slope here if we write, then this SF is equal to, say this is SF, then SF into delta x will give us this HF. Well, and then our this acceleration loss due to acceleration, that we could derive as 1 by g, then del v del t into delta x. And then this acceleration loss is per unit weight, and we are writing all this head. You can see this energy we are writing in terms of per unit weight. That is why we did calculate this acceleration also in terms of per unit weight. So, and that expression if we add here, then what will be our expression? That will be, say z1 plus y1 plus v1 square by twice z is equal to z2 plus y2 plus v2 square by twice z plus this HF we can write as now SF into delta x, then HA we can write as 1 by g into del v del t into del x. Well, now let me write this expression bringing all term in one side and putting a 0 on the right hand side. So this will implies and let us write it in this form, that y2, first we can write, say, y2 bringing on that side, y2 minus y1, because to have the expression, our main intention is to get a relationship so that we can have how the y are varying, how surface is varying. So, y we are writing first y2 minus y1. Then let me write this z, z2 is, if we bring here, this will be z2 minus z1. Well, and then let us write the velocity term. So, this will be plus, say, v2 square by twice g minus v1 square by twice g. So, we are writing each term in a different way with a intention, basically. We will write it in a very simple way. And then what we have, that is plus sf into delta x we have, then of course that term is remaining same, 1 by g del v del t into delta x. Well, now this y2 minus y1, that is the difference between depth here and depth here. This difference we can write as a small depth change, and that is why let me write this as del y. Okay, we can write it as del y, small distance, and this change in small elevation, let me write as del z. Then this we can write as del of, say, v square by twice g. Okay, and then other part will be remaining as it is. So, plus sf into delta x plus 1 by g del v del t into delta x. Now, if we divide this expression by delta x, dividing this by delta x, what we will be getting, say, del y del x, then this will be plus. Well, here we can make a change. What is that? Z2 minus Z1, that is Z2 here, if it is a falling slope, if the slope is falling in the downstream direction, then Z2 minus Z1, that will be basically always negative, because Z2 is smaller than that. So, if we consider that, then this small del z we can write as minus delta z. We can write it as minus delta z. That means, we are considering our slope to be falling. That is why we are putting this negative sign, as we know that z2 is smaller than z1. So, we are writing it. Then plus. So, well, this we will have to put here itself. So, minus delta z. So, delta z by minus delta z delta x, and then this one will be del x of, say, v square by twice g. And then this part delta x will be going off, then it is sf plus this delta x will be going out, then 1 by g del v del t. Well, now from this what we can simplify further? Well, on this side, as we brought all the expression to one side, here itself it is equal to 0, and here also it is equal to 0, and this is also equal to 0. We forgot to write the 0 on this side. Now, this can be written as well, let me write it here, say, del y del x is there, then minus sp plus, we had earlier, say, this expression we had del x of v square by twice c. Now, this we can differentiate. How? That twice v, then del v del x, that we can do. So, let us do that, and we can write it like that. So, twice v by twice g was already there, and so it will be del v del x plus sf plus 1 by g del v del t, this is equal to 0. Okay. Now, if we multiply this expression, if we multiply this expression or multiplying by g, so what we will get? Say g del y del x plus sf minus sb, let us put it here, sf I am writing first, then plus 2 and 2 is going out here. So, it will be v, g is already we are multiplying it. So, v del x, well then it will be del v del t plus del v del t is equal to 0. This is what the equation for, well, with SF and SB we did not have the term g. So, as we are multiplying it by g, this will be multiplied by g, and this is the equation of motion. And the standard way how we write this, we write the derivative of this t. Now, we are talking this as derivative, although we were writing this small increment earlier, and we are following the notation considering the very basic concept that, well, that v will be changing partially with respect to time. That is why we were putting the notation as del there to represent a small distance. Well, so then we can write this as, say, del v del t plus v del x plus g del y del x plus sf minus sb, that is equal to 0, and this is the required equation of motion. This is a simple way of deriving this equation. Of course, as I explained in the last class, that we can derive this expression starting from the momentum, starting from the Newton's equation of motion, and that way also we can get the equation. And so that sort of momentum equations are very popular, and we can write it in matrix form also, combining this, say, continuity equation and momentum equation, we can write it in matrix form, and that way it become more suitable for handling in computer programming. And then this equation that we are writing is basically for one dimensional flow, that is, we are considering the flow is one dimensional. So, when we are trying to equate energy, or when we suppose try to equate momentum, that we are doing in only one direction, momentum equation in one direction. But when it will be a two-dimensional flow, then we will be getting two momentum equations. So, that way our problem or the governing equation of this unsteady flow will be containing three equations. One is continuity equation, maybe in one direction x, then say momentum equation in x direction, then momentum equation in y direction, means lateral direction. That way we may get three equations, and solution of these equations are direct solution is not possible, and because these are all non-linear hyperbolic type, and so we go for generally numerical solution. And then when we go for numerical solution, lot of computer applications are necessary, and then we write this equation in matrix form, and that way we get it become more convenient for solution in a computer. And sometimes we simplify this sort of equation. Say this is our equation of motion. Well, this is our equation of motion. And now in this equation, if we consider the bed slope to be, say, very small, if we consider bed slope to be very small and suppose it is negligible, then this SB will become 0. Well, so our equation, from our equation, this term is going out. Then if we consider, say, SF, that is the friction loss is very negligible, suppose it is a short reach or somehow we are neglecting the friction, that will go out, then the equation will take a different shape. Again, in some case we may not consider some of these terms, and that without considering those terms, again SB equal to SF also we can get without considering these terms. Then it becomes simple equation SB equal to SF, that is the uniform flow, we were getting that expression. So like that we can have different forms in different way. And then with this equation, say finally what we can write, that this one dimensional governing equation we can write in this form. This is the continuity equation, and this is equation of motion. Well, and as we have explained already that solution of this equation or these equations are not that simple because of its form, and so that fully dynamic equation, this one, if we consider, then the solution of this equation become complex and we need to take recourse to numerical methods, and let us see how we can do solution of the governing equation. Well, the governing equations of unsteady, gradually varied shallow water wave equations are of nonlinear hyperbolic type. Well, and therefore, exact analytical solution of these equations, considering all the terms, as I said that okay, sometimes we can simplify this equation, but considering all the terms is difficult. I am not saying impossible, but it is difficult because people are doing different type of solution and someday they may get solution for this one direct. Then different numerical methods are used. So, what are the numerical methods? These are a method of characteristic which was started long back. So, method of characteristic is one popular method which is used for solution of any partial differential equation. Of course, that was applied to this solution of open channel flow equation also, and then that is why we are putting it here. And then finite difference method which is used popularly, and finite element method which is also used for solution of these equations. Then finite volume method is another method which is used. So, that way different methods can be used. Well, now we will be concentrating, so far our this particular course is concerned, we will be just discussing some of the aspect of this characteristic method of characteristic, not all. Well, because these we are keeping for higher level of study. Well, so method of characteristic also will not be discussing in detail. So, Mong in Paris developed a graphical procedure in 1789 for integration of partial differential equation. In fact, this method of characteristic initially it was given as a graphical procedure, and then it was for solution of partial differential equation, for integration of partial differential equation, and he named this procedure the method of characteristic. So, that it came long back in mathematics. Then of course, the Masao and Cray and Isaacson, they applied this method for analyzing flood wave in open channel. Well, now you may have some thinking that, well, how then still it is remaining popular. It was a long back that in 1789 it was started, people have used this in 1889, and why still it is being used? Yes, because starting from method of characteristic, Ritter, he did one solution in 1892, long back. He did this solution for dam break flood wave simulation, he did this solution. Then we started this problem, and we could see that for dike failure, to simulate the dike failure flood, suppose the flood is moving from the river due to failure of a river dike, in that case we do not have a solution, or we require a solution say for to fit into the initial part. Later on we can take it numerically, but the initial solution is important in some aspect. In that case we did use this starting with this characteristic method, so we provided a solution for say dike failure problem. So, using this characteristic method, Ritter gave for dam break and we gave it for say dike break flood. And then another importance why still it is gaining popularity, because or still it is in use, because say when we use numerical methods, finite difference methods suppose we are using, then always we find problem in solution of the boundary problem. Say we have a flow domain and we want to solve that flow domain, what are the value at, when we are talking about solution of flow in unsteady flow, we are meaning that what is the value of depth, or say what are the value of depth and velocity at a particular section, or at a particular section x means space we are talking about, at a particular space x, say spatial point x, and then at particular time. So with space and time, these are changing. So our challenge is to get solution for any point and at any time. So when we try to do that by numerical method, yes, we can get solution for some grid, and that grid point, if we make very close, it become almost solution for the, it represent the solution for the entire domain. So okay, in between the grid also we can solve sometimes. And then say, but when we apply those methods of solution, then we find that at boundary we many a time we find problem. And this characteristic method or method of characteristic help us in getting the solution for the boundary. And that's why we need to study this method and the very basic concept of this characteristic method, so that we can, if we go to the higher level, say other method, when we apply, then we will be able to use the advantage of this knowledge of characteristic method. Well, then method of characteristic, what it is, what is its basic way of doing is that this is a technique of converting a problem of solution of two nonlinear hyperbolic partial differential equation into a problem of solution of say 4 ordinary differential equations. So for our water problem is concerned, say we have two nonlinear partial differential equation. One is continuity equation, another is the momentum equation or say energy equation. Now these two equation, partial differential equation, nonlinear hyperbolic type, we cannot have a direct solution by direct integration. So if we can convert it, these two equation, into ordinary differential equation, then our task is simplified. So that is done by characteristic method, and then we can plot those graphically, and this gives us solution at certain point. Well, we will be coming to those points. So let us take the governing equation, continuity equation and equation of motion of unsteady flow in a rectangular frictionless horizontal channel. Earlier we were writing the expression, as you can see here, this is our expression, say del A del T del V del X, V del A del X, and this is the equation. If this equation is considered as horizontal, means this is going, and frictionless means this term is going, SF and SP will be going out, and then our equation will be a little simple. Okay. So let us take this equation for this one, and we will be, as we are talking about that, we are writing this for a prismatic rectangular channel. If we write it for a prismatic rectangular channel, then again this will be further simplified. So we will be starting with this expression. Say first let us take this expression, say del A del T plus V del A del X plus say A del V del X is equal to 0. So this equation, continuity equation first, and this we can write say del B into Y, well B into Y del T plus this V we can write B into Y, and then that we can write, sorry, V is V, A we can write del V, and then A we can write del B into Y del X plus this area again we can write B into Y, and then it is del V del X, that is equal to 0. Well, now if it is a prismatic channel, so this part we are writing for rectangular, this part we are writing for rectangular, and then for prismatic channel, what is that? For prismatic channel B is not varying with X, means with distance our width is not varying, because the very basic definition of prismatic channel is that the sectional dimension will not change or does not change in the channel reach considered. So this B is not varying, and as such what we can have, that is B we can bring common and we can write it in a different way, that is we can cancel B rather. What we can write, this is del Y del T plus V del Y del X plus say y del v del x equal to 0. So, this is say equation 1. Well, now again for rectangular, because we will have to write for the same situation, rectangular, prismatic, as we are writing once. So, we will have to write it for all, say rectangular, prismatic, then say frictionless channel, frictionless. Now, we will be writing equation of motion, frictionless, then horizontal, all these are there, horizontal channel. Now, we should remember that we are doing it for a very simplified situation. So, it is a simplified solution of course, and then when we go for considering all these things, then this sort of simple solution will not be applicable, but this gives us a preliminary idea how the flow will be or where the flow will move. So, this if we use, so what this means, that is our SF is equal to 0 and SB is equal to 0. Well, considering that, the motion, equation of motion can be written as, so equation of motion, that is what we did derive earlier. So, in this equation, if we just write in a simple form, that will be say del V del T will be coming as it is, then plus V del X is coming, then we had G del Y del X and other term SF minus SP. So, here those term will be going out and we are having G del Y del X equal to 0. So, this let us give as equation 2. So, we are taking two equation in a simple form, neglecting that there is some friction in the channel, neglecting that there is some definitely slope in the bed, but we are considering that slope to be very small, or we are considering this to be horizontal. So, neglecting those things, we can write the equation of motion in this form. Well, now we know that for rectangular channel, celerity, because wave will be moving in these sort of channels now because it is unsteady flow. So, celerity what we have, that we have, it is a shallow water equation. So, celerity C we can write is equal to root over G y. So, starting from this equation, as I did say, it is called Lagrange's equation of celerity that we did mention in our earlier classes. Well, now starting from this equation, here let us try to replace del y in this equation and say y wherever is there, y is there, y is here, then del y is there. So, del y and y let us replace and let us try to have it in the form of C. We have a very basic intention why we are trying to do that. Well, so how we can do that? That from here we can write that C square is equal to G y. So, simply if we just do say twice C del C del y, means taking derivative with respect to y. So, twice C del y, this equal to G, this equal to G. Well, so from here what we are getting, basically we are trying to get, this will give us one relation, that is y is equal to C square by G. This is giving us that expression, and we are, our interest is to express this del y in this term. So, this will give us one expression, that is G del y is equal to twice C del C, twice C del C. So, if we want to replace this del y, then we can replace it by twice C del C by G, or somewhere if we have a term G del y, because in some places we have term G del y directly. I think this is G del y, that we can replace by that term directly, and where we do not have G, then we will have to divide it by G. Okay. Or say this will that, okay, let me keep on writing that one, say del y is equal to twice C by G del C. Well, now putting, or say we can say replacing the value of y and del y in terms of C, celerity, in terms of celerity C, in equation 1 and 2, in equation 1 and 2. What we can write, that equation 2, if we write, say that will become, because here we have only this term, so equation 2 will become, say, del v del t plus v del x plus, we had the term here g del y del x, that we can write as twice c del c by del x equal to 0. Okay. And let us put this as, say, equation A. Okay, let me put this as equation A. And then writing in equation 2, this actually equation 2, and then equation 1, that let us see what we can write. If we put del y and c value, that will become, say, twice c del c by g. The term del y del t will become this one, because you can see this this first term del y del t, del y we can replace as del y is equal to twice c del c by g, so twice c del c by g, and del t is remaining there, plus v, then it was, the term was v del y del x, again del y we need to replace by this term, so it will become twice c del c by g del x plus then y, so y is equal to c square by g, this term, we had a term y here, y is equal to c square by g, and then we have del v del x, this is equal to 0. Well, so after that, so del v del x equal to 0, then we can further simplify this expression, like, say, well, some of the terms we can just cancel and make it simple. If we multiply by g this expression, then g is everywhere, so it will get cancelled, and then we will be getting this term in the form that twice c, okay, c is also there everywhere, so we can cancel that. So what we can write this expression as, well, g we are cancelling here, then c we are cancelling here, and then here c square, so this square will only get cancelled, and this expression will become, say, twice del c del t plus this will become twice v del c del x plus this term will become c del v del x, that is equal to, say, 0. Well, so this equation let me give as equation B. Let me give as equation B. Now, this A and B, here we are writing in the form that in the equation A, this is actually equation of motion, this part is coming as equation of equation of continuity equation, this part is continuity equation and this part is momentum equation. Well, now here you can see that this equation B, we have del v del t here and del c del t here. So, and here we have del x, so here we have twice v del c del x, and here we have v del v del x, and here we have again del c del x, here we have del v del x. If we sum up this term, then we can write a different equation. So, adding one A and B, so what we can write, that adding equation A and B. So, if we sum up equation A and B, then we will be getting this as, say, del v del t plus twice v plus c, then del c del x plus twice del c del t plus v plus c del v del x is equal to 0. Well, so we are just summing up these two equation, and each of the term we are just adding, t term being together, we are writing here and then here. Okay, this is the term. And then similarly, if we subtract this equation from, that is a minus b, if we do, then we will be getting a different expression. So subtracting a minus b, if we just do that, then we will be getting, say, del v del t will be there, then minus twice v minus c into del c del x minus twice del c del t plus, say, v minus c del v del x equal to 0. Well, now this equation we can give some name, say this is equation C, and this is equation, say, D. Well, this equation C, let us take first this equation C, and let us see how we can express this equation C. So equation C means the equation that we have obtained by adding this part. Now how we can write this? Say del v del x term, if we just keep in one side, and del v del t term if we just keep in one side, then let us see how we can write this expression. Well, say this part we can write as, or rewriting, let us write rewriting the equation C, what we can write, that v plus c into del v del x, v plus c into del v del x, that means this term v plus c into del v del x, plus again if we put this v plus c here, then we can write v plus c, that means just we are trying to bring some similarity here, we have some intention, v plus c, and then we can write twice del c del x, or del twice c del x, that is also we can write, and this we are putting like that in one bracket, then plus, then what are left? So del v del t, del v del t is left, plus this term is left, del v del t is left, and well, this del v del t is left, and then we are left with twice del c del t, or we can write this as del twice c del t, fine, and this is equal to 0. Well, this term we can write it in a different form. How? Say we can write it like, say, v plus c we are bringing common, suppose, and then it become v plus twice c of del del x. So we can write del del x of, say, v plus twice c. That is what our intention to write. So we are getting it in this form, and then plus this term we can write as del del t of, say, v plus twice c. So interestingly, we are getting this expression here also as del del x of v plus twice c, and here we are getting del v plus twice c. So v plus twice c and v plus twice c is common, and here we are getting in terms of derivative of this with respect to time t, partial derivative, and here we are getting it in terms of partial derivative of this in terms of x. We know that this v and c, in fact the velocity v and the celerity c will be always a function of x and t, will always be a function of x and t. Now if we consider this as a single variable, say, then this particular expression is giving up us another option of, say, simplification, or another option of simplifying this. If we consider this as one expression, just if we see the similarity, suppose a variable, this equation we can further simplify as said, say, let us take this example. Suppose if we have a variable, any variable, say, okay, let me write this as the variable, and which is a suppose function of x and t, then what we can write? say if it is a function of this, then we can write say d of this variable, we can write as okay, this d of this variable we can write as say del of this variable divided by del x into dx plus say del of this variable by dt into dt. Now, what the similarity we have if we take say dv dt, this I mean this v we are taking, and then what we can write say this of this variable x and then we are having dx dt plus this del t. So, what this variable is? Actually, we are talking about this variable as v plus twice c. Suppose our this is equal to v plus twice c. If we consider this as v plus twice c, now we see if we write this variable and we know that this is a function of x t, and then we can write it in this form. So, what we have seen finally that in this equation, if we now put this part, then we can see sorry, this is dx dt. This expression is almost similar to that. Say del del x of this term and we are having del del x of this term. Okay, let me write this here. Say del of v plus twice c into del x, and then of course we have dx dt, and plus here we have del of v plus twice c into del t. So, this expression is similar to this one, this expression is similar to this one, v plus twice c and del t, fine. And this part. So, what is not matching this equation and that equation? If we compare, then what is not matching, that here with this term we have dx dt and here we have v plus twice c. That is the only difference between these two forms. So, now if we can have the dx dt is equal to v plus c, then these two equations will be identical. So, let us do that. Considering dx dt equal to v plus c, that means if we put dx dt is equal to v plus c, then the equation, say let me give a name to this equation, then it is say E. The equation E the equation E is identical to the above equation, means this equation. So, what we can write, this is what we are getting basically, say total derivative of this with respect to time t, say total derivative of v plus twice c with respect to time t. So, that we are getting. So, the it is identical. So, if it is so, our expression is actually equal to 0. We are getting this expression is equal to 0. This is equal to 0. So, this is also equal to 0. So, this expression is equal to 0 means here we can write that this expression is equal to 0. So, what we can write, that means d of v plus twice c by dt is equal to 0, but this will be valid, and that expression we are writing like that, this will be valid when when dx dt is equal to v plus c. So, we are getting, and this will be actually when say total derivative of v plus twice c is equal to 0, that means what? This implies v plus twice c is constant, v plus twice c is constant. Okay. So v plus twice c is constant, and along with that we will have to have this equation dx dt equal to v plus c. So these are the combined equation. Actually, when dx dt is equal to v plus c, on those points where dx dt is equal to v plus c, there only we get that v plus twice c is equal to constant. Well, and similarly, if we take the other equation, that is the equation d, by subtracting what we got, this expression. So similarly, from equation d, what we can get? Similarly, from equation d, we can get v minus twice c is equal to constant when dx dt is equal to v minus c. So these equations are basically the ordinary differential equation that we are getting. We started with partial differential equation, but we are getting ordinary differential equation, and we are getting 4 equation in this form, and then this contain ordinary differential equation only here, and this is of course straight equation and difference equation only. So this gives us a better opportunity for solution of the problem. Well, now let us see, this equation can be written as, say, dx dt is equal to v plus c, and then dx, okay, along with that I will be writing the other equation, that is v plus twice c is equal to constant. This is another relation, and then we are having dx dt is equal to v minus c, and here we can write v minus twice c equal to constant. Okay. And this equation is called characteristic equation, and this equation is also called characteristic equation. And this equation, as it is v plus c, so this is called positive characteristic equation. This is called positive characteristic equation, positive characteristic equation. And this equation is called negative, I am writing in brief, characteristic equation. Well, and v plus twice c is equal to constant, that is called positive Riemann invariant, that is called positive Riemann invariant, Riemann invariant, and this is called negative Riemann invariant. Okay. Because it is not varying, it is remaining constant. So now let us see, understand this point, that we can consider v plus twice c as constant only on those points where which follow dx dt is equal to v plus c. Now if we draw a plot, or if we make a computational domain of x and t, then we can have dx dt a line, and then that line at dx dt, that line is equal to actually v plus c. The slope of that line will be getting by v plus c. So v plus c will give us some value, that will give us the slope of that equation, and then accordingly we can draw a line, and on that line whatever point lies, at any point, if we take the v and twice c at one point, at another point if you take v1 plus twice c1 c, this all value will remain constant. So taking that advantage, we can solve for the this characteristic equation can be used for solution of the governing equation. Now let us see how we represent this graphically. Okay. So graphical representation means, if we just take xt plane, so this is our x and this is the time t. Okay. In xt plane, say we are having a line dx dt equal to v plus c. So from that we can have a line like this. Say this is suppose representing dx dt is equal to v plus c. Then we will call this as a positive characteristic. So on that line, if we take suppose x at a particular section, this one, and if we just make some division here, say this is a point and this is another point, another section, these are some section here, okay, and this is going characteristic line, okay. Now suppose if we know, say at time equal to 0 may be the steady state, time equal to 0 may be the steady state, then unsteady has started. So with time this flow will be changing. Now at initial, at unsteady flow at steady flow condition, suppose we know this value at x equal to suppose some value x1, we know the value of the variable. What are our unknown value? Unknown is our v and t. Our unknown is the depth and velocity. So at suppose this point we may be knowing, say this is p, let this point be p, and suppose we know this value v and y, these are known here, and we know that this is the v plus c. So v plus c is equal to dx dt. So accordingly we are drawing this line, and then say at another time level, suppose t1, we do not know because unsteadiness has started and we want to get solution what will happen at time t1. At this time level we have this point, say this point is q, okay, let me write it as r because I will be writing another curve on that side. Suppose this is r, and at this point what are the velocity and what are the depth, that is unknown, that we do not know at time level t1. But we know one relation, that if I put this as v r and y r, so what relation we have? Because along this line we know that v plus twice c is equal to constant, v plus twice c is equal to constant. So v, say at p, plus twice c, c is nothing but twice root over say g y p, this is nothing but c, this is equal to say v r plus twice c r, okay, let me write it as c r first, then so that you may not confuse, this is say c p and this is c r. But what is c p? That c p is nothing but say v p plus twice root over g y p, our unknown quantity is actually y, this is equal to v r plus twice root over c root over g y r, root over g y r. So as these, now these equations are there and our unknown quantity is this one v and y, but we need to solve for two unknown quantity, one is that v r, one is that another is that y r, but two unknown quantity we have only one equation. Now if you use the negative characteristic curve, then we can have that negative characteristic curve in this side, this will be coming like this. How it is coming like this, that I will tell again, because this will be coming like this for shallow for say subcritical flow. Why? That I will be explaining when in the next slide. But if this is say q, then this is say vy, and vq and yq is also known because it is at the time equal to 0, initially we know. So now if this negative characteristic line is passing through this one, we can write this as say dx dt is equal to v minus c, that is what is negative characteristic line, okay. Now from this again we can get one relation between this and that. So what we can have, that another relation we can have is that vq plus twice root over g yq is equal to vr plus twice root over g yr, because it is passing through the same point. And then using these two equations, now we have two unknown, we can solve for this particular point. So that is what the beauty of characteristic method, and we can solve this once we know this value. Then similarly to solve what is the value here, we can get the solution here. Similarly we can proceed to solve this one, we can get here and here. But to solve this one we need some boundary solution or boundary relation. What is the sum condition here? Of course, we will be getting one negative characteristic line. This will be giving us one relation between this and that, but we need one more relation. Okay. Now, let us see for subcritical flow. Say for subcritical flow, as we know that V is less than equal to C. When V is less than equal to C, dx dt equal to V plus C, that is the positive characteristic line, this will be slope will be positive. So, this will indicate that slope is positive. And dx dt, say what is negative characteristic line? Negative characteristic dx dt equal to V minus C. This will be having, say as V is less than C, so this will be having negative slope, and that is why when I was drawing for subcritical flow, if I draw the xt plane, this is the time, this is x, then for supercritical and subcritical, or for subcritical, we will be getting the positive characteristic line this, negative characteristic line this. This is the positive characteristic and this is negative characteristic, and that is why earlier we were drawing this is positive, this is negative. Well, then okay, this is not the only line, we will be having several set of line like this and several set of negative characteristic line, because at different point we will be having different situation, and that will lead us to several line. Okay. Then in case of supercritical flow, V is greater than C. So, positive characteristic, say dx dt equal to V plus C will be definitely positive, but negative characteristic dx dt equal to V minus C, but that negative characteristic line will also have positive slope, So, this positive means we are talking about positive slope in the xt plane. So, this we are drawing in xt plane because V is greater than C. So, V minus C will also be having positive slope. So, if we just draw it here, then we will see that, but which slope will be greater, that because V and C it is plus. So, this positive characteristic line slope will be greater, and so positive characteristic line slope will be going like this. So, greater means it is we are writing dx dt, not dt dx. So, t is in this, x is this. Slope more means it will be from the t line. So, it is going the positive characteristic and the negative characteristic will be going like this. It has less slope. Okay. From our general concept, we may have a feeling that this is having higher slope, but it is with respect to this line we are talking about slope. So, this will be having less slope. So, it is negative characteristic. So, that way we will be getting series of curve like that. And then this is the case when say flow velocity and wave are moving in the same direction. If the flow velocity and waves are moving in the opposite direction, then V become negative, then our curves become, both are becoming negative slope. So, both are becoming negative slope, positive characteristic are also becoming negative slope, because V is this time negative and with respect to C. So, V minus C means minus V minus C, that will be steeper and the other one will be flatter. So, like that we will be getting positive and negative characteristic curve, both are sloping upstream, and this sort of things become more important when we go for numerical solution of this point. Now, just to finish this one or to complete this one, if we say that for critical condition what will happen, say for critical condition what will happen, at critical condition V is equal to C. So, when V is equal to C, our positive characteristic line, fine, this will be having a positive slope. But what about negative characteristic line? Positive characteristic line will be having this one. But for negative characteristic line, V minus C. So, as V and C is equal to 0, so dx dt is become 0. So, dx dt 0 means with respect to this axis we are talking about t and x. So, this line will be just vertical. So, this is the negative characteristic line for critical slope. Well, with this limited time we have just tried to give you some idea, or rather we have discussed about some idea of this characteristic method and how these things can be helpful in solving some of the problem and that way we could cover at least very preliminary of this part, and there are a lot of things to be discussed in this line, and then how these are applied for actual solution. This also need discussion, that are of course we are keeping for higher level of study. And for unsteady flow in our discourse, let us conclude here, and from next class onward we will be moving to a different topic that will be related to pipe flow. We are still till today we are doing with the open channel flow. From next class onward we will be moving to pipe flow. Okay, thank you very much.